Welcome to day 2 of vectors. We're going to do more work with vectors, and we're going to talk about something called dot product. First, reviewing a vector. A vector is both magnitude and direction. And a couple of examples here: 40 miles per hour southeast. A force at a certain angle. Our notation for vector is a V with a little arrow hat on it, and we always write a vector like this. The vector has components, has an x and y component. So an example of a vector could be pointy brackets, not parentheses, 5, 3. And that means the vector starts at 0, 0 and ends at whatever point is given for the components for x and y. Two important details for vectors. So we have component form, which is the x and y component, and then we need to know its magnitude and direction. Magnitude is its length or distance. So I use the Pythagorean theorem, which is right here. And the other important component is its direction or angle, and I use inverse tangent to figure that out. We measure the angle from the positive x-axis, and when we do this inverse tangent in our calculator, we need to make sure that whatever angle we get on the calculator matches the quadrant of our component form. The inverse tangent can only give two quadrants: quadrant 1, positive angles; quadrant 4, negative angles. So if a vector is in quadrant 2 or quadrant 3, we have to add 180 degrees to that angle. A quick little example is vector V, or what I'm calling vector RS, 6, 5, which is definitely in quadrant 1. So its magnitude is the Pythagorean theorem. I don't have to use negatives with the Pythagorean theorem, so 6 squared plus 5 squared, we didn't have any negatives anyways. 36 plus 25 is the square root of 61, and I'm going to round it to the nearest tenth. It's kind of going to be the theme for this unit. 7.8 is its length, and then theta is going to be, let me change colors, it's going to be inverse tangent of the y over the x, and I get 39.8 degrees, and let's see, 39.8 degrees is also in quadrant 1, so I'm good. So when we have components, x's and y's, I could figure out the magnitude and its directional angle. So now we're going to talk about a unit vector. A unit vector is a vector that has magnitude equal to 1. And we have two special unit vectors, one for the horizontal and one for the vertical. And it's the letter I for the horizontal because this is an x component. And the letter J is the y component. And it's just very special ways in which I could label vector. So over here on the grid you could see vectors I and vector J. Vector I is length 1, it's in the x direction, and is the vector 1, 0. And vector J is again a length vector 1, this in the y direction only, so 0, 1. So when I see vector 6, 5, I could rename it as 6i plus 5j, and these two things are the same thing. 6, 5 is in component form. This form is we're going to call something else, but I could prove that they are the same. 6i plus 5j really means 6 times the vector 1, 0 plus 5 times the vector 0, 1, which is equal to 6, 0 plus 0, 5, which is really equal to 6, 5. So there's two ways to name vectors. Component form, that's what this is, when we have them inside the pointy brackets and just the numbers. And we're going to use component form probably most often. But we do need to know this other form, and this other form is called linear combination form. just using i's and j's. Don't get caught off that i's and j's are something fancy. I is just the unit vector in the x direction, and j is the unit vector in the y direction. Okay, so on the previous page, I gave you component form, and we could figure out its magnitude and direction. How about if I give you its magnitude and direction, and now we got to figure out its component form? Well, we're just going to use trigonometry, and I think you remember things from the unit circle, that the x value was just cosine and the y value was just sine, or when we went beyond the unit circle, that x was equal to r times cosine and the y was equal to r times sine. Well, those are the equations we're using. We are using the x component is equal to the vector times cosine of whatever angle is given to us, and the y component is equal to the vector times sine of the direction given to us. So if we look at our picture of what a vector looks like, we have a vector. This is the vector here. It has an angle. It has an x component. It has a y component, which is combined right here. And if you look at trigonometry, that cosine of an angle is adjacent over hypotenuse. You get vx over v, and sine of theta is equal to opposite of hypotenuse, which is vy over vector v. And I could get rid of the vector v's on the denominator by multiplying through, and we get our two equations here that we were looking for. Okay, so on the front page I gave you component forms, and you gave me magnitude and direction. Now I'm going to give you magnitude and direction. You're going to give me the component forms, and that's what we're working on. So we should do an example. When we do examples, make sure our calculator is in degree mode. No radians. You guys should be happy. So for this example, I should draw it out first. I have vector v, which is at 300 newtons at a 120 degree angle. That's 120 degrees from the positive x-axis. So I have my given information. Here's my picture. My x component is going to be my 300 vector times cosine of 120 degrees. My y component is going to be 300 times sine of 120 degrees. I put that in my calculator, and I get these results. And if I write it in component form, I get negative 150, come at 259.8. Let's see, negative 150, 259.8 is in quadrant 2. And let's see, 120 degrees, that's in quadrant 2. They do match. You should always make sure that happens. And I even drew my x and y components on the picture in pink, as you can see, to match up what I have. And that's all we're doing. We're going from front page, or what we did last class was we had x's and y's, and we made magnitude and direction. Now we have magnitude and direction, and we're going to make the x and y components. So we're going to talk about compass directions. We're going to establish that 0 degrees is due east, which is really the positive x-axis, and 90 degrees is due north, which is the positive y-axis, and so on and so forth. So when I have a vector that's at 250 miles per hour at southwest, well, southwest is in between south and west, which is between 180 and 270, which is 225 degrees. So here's 225 degrees. This is 250 miles per hour. And let's see, at 225 degrees, and I could break it down into my components. This is all calculator work. We just plug things in our calculator, and x is using the cosine key, and the y coordinate is using the sine key. Well, this is going to be in the middle, so they're going to be the same. And if I write this as an ordered pair component form, I get negative 176.8, negative 176.8, and let's see, this is definitely in quadrant 3, and 225 degrees in quadrant 3, so that matches. And you can see in pink I drew the x and y component, and they should be about the same, and they're both negative. So I call the equations the big four equations for vectors. The first two is when I know my components, I can find magnitude and direction, and the second one is when I know my magnitude and direction, I could find my components. We're going to use these four equations all the time. The next item we're going to do is called something called dot product. Dot product looks like it's multiplication of vectors, but multiplying vectors is actually something different. It is actually, we are multiplying, but we're just multiplying the x components and the y components individually, and then we're adding them together. So when we're done, we don't have a vector anymore. The result of a dot product is a scalar, not a vector. That's the big key. So you could see vx, vy, wx, wy, multiplying the x's, multiplying the y's, adding them together. We'll do an example here that if I want to find the dot product, and you can see it's a solid dot. It's going to be the x values, 4 times negative 2 are the 2x values, plus the y values, 3 times 1, which is negative 8, plus 3. So vector v dot vector w is equal to negative 5. It's not a vector any longer. It is just a scalar value. Let's do another example. So we take our x's and we multiply them together. Plus we take our y's and multiply them together. I get negative 8 plus 8. So in this example, v dot w is equal to 0. For me, that seems sort of special. So let's draw these vectors on this grid and see what's really going on between these two vectors. So here are the two vectors, v and w. I plotted them out, and if you see the relationship, I think if you look closely, they are perpendicular to each other. So, what can you say about these two vectors? Vector v is perpendicular to vector w. So if the dot product is equal to 0, we could say then the two vectors are perpendicular to each other. So how is dot product useful? It helps us determine the angle between the two vectors. So if I have two vectors, I can help determine this angle between them by using dot product and using this formula. Cosine of theta is equal to the dot product divided by, when we multiply, the magnitudes. Or if you want, you could say theta is equal to inverse cosine of the dot product divided by magnitudes and we're always going to get an angle when we do inverse cosine. Let's do an example. So here are my two vectors, vector v and vector w. I'm going to rewrite w in component form, so I have to remember that this linear combination form can always be rewritten as component form, and it's negative 2i, which is the x, and then it's really a 1j. And then maybe now it's easier to figure out his dot product, and actually this is an example we did before. Multiply the x's plus multiply the y's. I get my dot product is equal to negative 5. So that's part of the things that I need to do. Now the next thing I need to do is the magnitude for v and w. So the magnitude of v is going to be 4 squared plus 3 squared, the square root of. So my magnitude of v is equal to 5. That turned out nice. Now I have to do the magnitude of w. Well, that's going to be, I don't have to do negatives with magnitude. You could do -2 parentheses squared. I could just do 2 squared plus 1 squared, the square root of. So the magnitude of W is the square root of 5. You could just leave it that way because when I put this in the calculator, it handles everything nice. So when I'm done, I could do cosine theta is equal to -5 over 5 times the square root of 5. Or better yet, theta is equal to inverse cosine -5 over 5 square root 5. And because when you put this in your calculator, either use that fraction bar key or put parentheses around the denominator. When I'm done, I get theta is equal to, according to my calculator, to the nearest degree, I get that result. That means if you drew out these two vectors, and you could pretty easily on a grid, you would see they're 116.6 degrees apart from each other. So this last page is just more examples of going from having our vector and our direction, our magnitude and direction, and making it to components. This is going to be very helpful tomorrow when we start using applications of why we do vectors and why we break them up into components. So I'm going to call this first vector A, and it would be 30 cosine 25 degrees, 30 sine 25 degrees, and my vector B would be 50 cosine of -70 degrees, 50 sine, -70 degrees. And I can put these both into the calculator, and they'll just spit it out, and I just round to 1 decimal. So I put them into the calculator, and this is what I got. And when I'm done, I should always check the quadrant. Vector A, these points are in quadrant 1, and that angle 25 degrees is in quadrant 1. And vector B is in quadrant 4, and this angle of -70 degrees is also in quadrant 4. They match. I'm in good shape. I think that's an easy, what I call 5-second check to make sure we're doing things correctly. So I have my airplane flying at 500 miles per hour at 20 degrees. 500. Oh, that's terrible. And my eraser. Cosine 20 degrees. 500. Sine of 20 degrees. And so my vector A is equal to 469.8, comma 171.0 when I round to 1 decimal. And I should always check the quadrant. And I'm pretty sure that this is in quadrant 1 and 20 degrees is in quadrant 1. So that does work out. My wind is -42 degrees at 40 miles per hour. 40 cosine -42. 40 sine -42 degrees. And I put that in my calculator, and I get my wind is going to be 29.7, comma -26.8, rounded to 1 decimal in component form, because component form is very important, especially tomorrow. Let's see. Positive x, negative y, this is quadrant 4, and -42 degrees is in quadrant 4. Everything matches.